Okay, that went okay. First video seems pretty good. So moving on to the second question here. So the second question, we've got a table of data. Data below were collected for the following reaction. So we're given the reaction, and we've got a nice table of data. So hopefully you recognize this as the data we would use to figure out the rate law for a reaction, right? And if that is exactly what part A here asks for, right? The expression for the rate law. Now, the general form for rate law, which we should be pretty familiar with now, is rate is equal to the rate constant, and then there's a term for the concentration of each reactant. So CH3Cl, methyl chloride, and chlorine is the other reactant. Just the reactants for rate law. That's kind of a contrast with what we'll see for equilibrium. But now there's an exponent that goes with each of these concentrations. And that exponent relates to the mechanism of the reaction. It kind of tells us about the steps involved in how the reaction actually happens on a molecular level. So what we want to do with the data in the table is figure out the identity value of those particular exponents, and we do that by an observed change in concentration of one of the components and recognizing what that does to rate. So if we go back to the table here and try to figure out what's going on in the table, what I'm looking for is two versions of this reaction where the concentration doesn't change. So if I just look at the first two here, chlorine is not changing between experiment 1 and experiment 2 here in the table. And that's good, because if I know that chlorine stays the same, that allows me to focus in on how does the other reactant, the methyl chloride, affect the rate. So chlorine was the same there from 1 to 2. And if I go from 1 to 2 here, the concentration of the methyl chloride doubles. So I'm seeing a doubling in concentration, and then if I look at what happened with the rate, 0.014 to 0.028, the rate also doubled. So what I'm really doing here is I'm comparing this whole equation for both runs of those experiments. But if you do this correctly, almost all the information cancels out except the rate and the concentration that you're changing. So if I take rate 2 divided by rate 1, that's equal to 2. Right? And then I take the concentration of methyl chloride for number 2 divided by number 1, that is also 2, but I raised methyl chloride to the xth power. Right? Now, comparing these, the rate constant's the same for both runs, concentration of chlorine was the same. That's how I'm able to simplify it like this. If 2 is equal to 2 to the x, that means x as an exponent has to be 1. So I now know the exponent that would go with the methyl chloride here, reactant in my rate law. That's going to be a 1. I need to do the same thing here for chlorine. So if I want to evaluate the effect of chlorine in terms of the rate law, how it changes the rate, I need to find a place where the other component doesn't change, and that would be experiment 2 to experiment 3. They both have 0.100 molar for the concentration of the methyl chloride. So that's the same. If that's the same, I can evaluate whatever change might appear here for the chlorine in my reaction. So 0.05 to 0.1, that's doubling. So the concentration of chlorine doubled between those experiments. I can look for what effect did that have on the rate. So 0.028 to 0.112, that looks like about 4 times faster. Now let me divide it out just to be sure. 0.028, and it does come out to exactly 4. That won't always be the case, but 4 times faster. Now if I do the same simplification here, since I kept the methyl chloride the same, that's all going to cancel out. K is going to cancel out. If I ratio my rates, 3 over 4, right, and I would say always do the version that gives you a number as opposed to a fractional number. If you put 1 over 4, you get 0.25 or a quarter, and I just find that's a little harder to evaluate the exponents. The concentration ratio was only 2 though, So what does that mean for the exponent? We called it y in the original equation. If 4 is equal to 2 to the yth power, that means y is equal to 2. So this reaction is going to be first order in the methyl chloride, second order in the chlorine. So rate law is rate equals rate constant, concentration of methyl chloride. Now, raising something to the first power is the same as not writing in an exponent, so either way is appropriate. There's no need to do it one way or another. I kind of like to write in the 1 because now it's clear to me that, yeah, I did go through and solve for that one. If you leave that 1 out, you might forget to check it. Maybe you don't really know if it was really 1 or not. The other thing here, I find people a lot of times leave off a whole half of this equation. If you don't write rate equals, you really haven't written the rate law or the rate expression. If you just write k, this to the first power, this to the second power, it's not even an equation. So it's not describing completely what happens in the reaction. So you should always have rate equals on one side of that equation when you go to write down what the rate law is. Now, rate being on one side of that equation is important for part B, because for part B, we want to calculate the rate constant. Now, rate constant is the same for every time you run the reaction. So you could use any of the experiments up here in the table. I'm going to use experiment 4 because I feel bad for it because it's been left out so far. We didn't use it for any of the comparisons. But since it's 0.2 for both of them, that's also going to make the multiplication a little bit easier. So taking this equation, if I want to solve for k, I'm just going to have to divide through by the concentrations here. So on one side, I'll have rate divided by the concentration of methyl chloride and divided by the concentration of chlorine squared. And that will just leave k on the right side of this equation. Now I go back up, and all from the same equation, I pick out those pieces of information. 0.896 for my rate, and it's 0.2 for my methyl chloride concentration and 0.2 for my chlorine concentration. I certainly don't want to forget to square that. So if I punch this in, 0.896 divided by 0.2, divided by 0.2, divided by 0.2. Right? Maybe if you're good with your calculator, you can do it a little more efficiently than just dividing by 0.2 3 times, but I'm comfortable with that with my little $9 calculator. You do the math here, you get 112. Now, that's certainly part of the answer. That's the numerical value of the rate constant. But keep in mind, that's only going to be part of the points. The units on the rate constant are really important because they tell us about the reaction. This reaction being first order in methyl chloride and second order in chlorine is third order overall. We will have specific units on the rate constant because the reaction is third order. Now, rate is always, let me put it in the middle here, this middle space. Rate is always molarity per time. It was seconds here in this reaction, so molarity per second. Our concentrations here are always in molarity, so the reaction being first order in methyl chloride would be 1 molarity in the units. The reaction being second order in chlorine would introduce molarity twice, or molarity squared. The units on the rate constant have to add to the equation so that both sets of units on the right side and the left side of the equal sign are the same. That means we've got to cancel out 2 molarities in our units. So 1 over molarity squared would cancel out 2 of those molarities, so we just have 1 left to match what's on the left. We also get our time component from the rate constant. So the units on the rate constant are 1 over molarity squared seconds. The most common way to write that would be molarity to the -2, seconds to the -1. Right? But you could write that as 1 over molarity squared seconds. Or, if you want to get real fancy, so molarity is moles per liter. Let's flip that over, it's liters per mole. So liter squared, mole squared, seconds would be the third way you could write that out. And I kind of like that one because some of those only makes sense in relationship to the fact that we're describing a rate constant. Like mole squared doesn't really have a physical meaning in terms of squaring the quantity of stuff. It's only in relationship to the rate constant that means anything. But if you see one of these on a test, right, this numerical answer will be some of the points, but the proper units will also be accounted for in there as well. So keep that in mind. Okay, so that's about long enough for one video. We'll stop there before we go on to page 2.